Another video. Okay, so I'm making another video today, and this is not in the ongoing series that I'm doing about the discrete Fourier transform. But what happened is I'm just studying for these exams that I'm doing. It's in a long time, but I decided I should just study a little bit now and then, versus all at once later. And one of the practice exam questions was to prove the simplicity of the alternating group. Now, it's been like literally 3 years since I took a class in algebra where we proved this, and I remember the proof being like quite difficult to remember. Like I have no idea how I would come up with it in an exam setting, just because it's just kind of tricksy. So I spent like a couple hours today trying to learn the proof again and trying to convince myself that if I came up to it in an exam, I'd be able to do it. Just remembering a few key ideas. So this, unlike some other videos, this is one where I don't have my notes. I'm just going to try to do it. I did look at the proof before, or a proof, and try to like construct one. I mean, there's many proofs, but sort of look at one that I think that, a week from now I would still be able to remember, because I don't think it's the one that I learned in class either. Okay, but the three steps are one, if n is a normal subgroup. Okay, I'm also not going to do all the definitions because I assume you know, like, not all the definitions, but some of them. So, normal subgroup of Sn, or let's say An, a normal subgroup of An, and n contains a 3-cycle, then n equals An. Okay, that's one. That's the first step. And then the second step is we're going to prove A5 is simple. Okay, so this is already different from the one I learned in school, I think. But the one I learned in school has like this like trick that I like do not trust myself to remember. And then we prove An is simple for n greater than 5. And this is a slower proof, but hopefully one that's like more conceptual and less, or at least just easier to remember. Okay, so I'm going to try to do this now. Hopefully this is helpful for you guys also. So anyway, okay, so let's prove one. So these are the proofs now. Okay, so we want to prove that if n is a normal subgroup of An, and okay, so I guess let's talk about, first of all, I'm not going to define everything, but simple means that it has no non-trivial normal subgroups. Okay, so we want to show that A5 has no non-trivial normal subgroups. One way of doing that is by taking a normal subgroup of An and then showing that it has a 3-cycle, which means that n must be the whole of An. Therefore, An must be simple, right? Okay, so this lemma we want to show, so we assume, say, n contains sigma equals, we can rename everything so that it's 1, 2, 3. Okay, then I think since we have 1, 2, 3, we should be able to get 1. We should be able to get any, I know we need to get to, so there's still some computational tricks, but I do know we need to get to 1, 2k, because these generate An. Okay, so for any, let's say, for any k in 4 up to n, I think you do this. So we want 1, 2k, so 3 is going to be, so this 1, 2, 3. We want 1, 2k, so 3 is the number we're going to put here, because we put 2 or 1, then the output here wouldn't have a 2 or 1. So, right, because 3 goes to k, and then k goes to 3, so 3 doesn't show up here at all. But what happens is 1 still goes to 2, and then 2 goes to 3, 3 goes to k, and then k goes to 3, 3 goes to 1, and then So that shows that k goes back to 1. All right, so I'm trying to, as I remember, say how you could maybe remember it also. Okay, so but yeah, what I do remember is that the 1, 2 k's should make the rest of the group, because, why is that? Oh, because n is generated by 3 cycles. Okay, well, let's just do that. Let's just show first of all that we can get any other 3 cycle. So now that we have all the 1, 2 k's, let's try to get anything with a 1, I, and a j. Now this one I remember is pretty, oh, sorry, yeah, 1 ij. So this one I think it's like 1, 2 something, 1, 2 something, 2 something, and then 1, 2 something. And if I'm not wrong, it's j, j, I. J, j, I, j. Okay. Let's see. So 1 goes to 2, 2 goes to I, then I doesn't get touched, so 1 goes to I, and then j, I goes to 1, 1 goes to 2, and 2 goes to j, so that's correct. And then j goes to 1, 1 goes to 2, 2 goes to j goes to 1, so j goes back to 1, perfect. And then 2, 2 doesn't get touched, let's just check, 2 goes to j goes to 1, and 1 goes back to 2, so 2 stays 2. Okay, so this actually was correct. Now, this I remember now because I just did it, but honestly, I don't know what's a good way to remember this. Yeah, I mean, we got up to 1, 2 k's, and then now we want to put another degree of freedom by changing the 2 to be anything you want. And you know that's going to be a product of a 1, 2 something. And I guess from there, with a little bit of, you know, just messing around with numbers, you might be able to figure out that it's this. Okay, so already we see why this proof is kind of stupid to put on an exam, but that's not that's just my opinion. Okay, I don't really like memorization heavy things, which is why I'm trying to like talk through this and maybe see why. Yeah, it's just so many tricks. Okay, so all right, so that's 1 ij's, and so now we basically, because any permutation that any 3 cycle, sorry, that doesn't that involves I can be written as 1 ij. You just write it around. Now we just want things that don't have I. So that don't have 1. So let A, B, and C be all numbers from 2 up to n. And we want to write A, B, C. And I think this one's pretty easy. This is you can write it as 2 3 cycles that have 1 in them. I think. Yeah, this is, you know, it's I think it's 1 A, B, and then 1 B, C. That should be it, right? Because 1 goes to B, B goes to 1. So that's fine. So that's why 1 gets thrown out. But A goes to B, B goes to C, and C goes to 1, 1 goes to A. Okay, so now we've shown that any 3 cycle. So far we have shown that all 3 cycles are in n. Okay, so if we have 1 3 cycle, then we have all 3 cycles. Now we need to show that we have all of an, which means we need to show that any element in an can be written as 3 cycles. And this one is it is actually pretty easy. Okay, so an are even permutations, meaning that any element of an can be written as a product of an even number of transpositions. And so we just need to show that A, B, C, D, where these are both transpositions, can be written as a product of 3 cycles. Right? Any element of an has an even number of transpositions. So there's 3 cases. If AB is equal to CD, then these are the same and they cancel each other out. So then we get the identity, which is obviously an AN. Which is obviously a product of 3 cycles. It's the empty product of 3 cycles. If the, say, A, B, and C, D, this intersection has size 1, say they intersect at B without loss of generality. So I guess, let's say B equals D. Okay. Then AB CD is equal to AB. CD is just BC, which is ABC. So that's obviously a 3 cycle. Now last one, they're all different. So if A, B intersect C, D is empty, then A, B, C, D, this one, it's a product of 2 3 cycles. And the way we do it is we put, there's AB, there's something in between here. I think it's, we put BC twice. We can do that because BC is just 1. This makes it work. So AB, BC, that's ABC. And BC, CD is BCD. Yes, that's a product of 2 3 cycles. Sorry, I'm just going to wipe my nose here because it's annoying me. Not the best presentation, but okay. Now, okay, so what have we done? So we've shown that N contains 1 3 cycles, so it contains all the 3 cycles, and if it contains all the 3 cycles, then by closure properties, it must be all of AN. Okay, so that's actually done. We're done part 1. Okay. Okay, hopefully that was, I didn't write all the words in between there, but I think I said all the steps. Okay, so then 2 doesn't actually rely on 1 at all. 2 is, we prove A5 just by itself. Okay, and this I don't really remember. Okay, so a conjugacy class is a set of elements, all of which are conjugate. Remember that like T is like conjugate to, or tau is conjugate to sigma if like tau equals pi sigma pi inverse for some other permutation. Okay, now a normal subgroup is closed under conjugation, which means that a normal subgroup is a union of conjugacy classes. Okay, so a conjugacy class it's an equivalence relation if tau is conjugate to sigma, sigma is conjugate to tau, and all sorts of transitive things. So so all we need to do is like enumerate all the conjugacy classes of S5 and then show that the only non-trivial normal subgroup you can make out of those numbers is A5. Okay, you could also do this with A5, like just get the conjugacy class of A5 outright, but then you don't get the nice property that the conjugacy classes are exactly correspond to the cycle structures. Okay, so here's I'm going to explain. So there's 7 different types of cycle structures in S5. So you could have a 5 cycle. You could have a 4 cycle. You could have a product of, remember, these are disjoint cycles. You can represent a permutation by disjoint cycles. So it could be a 3 cycle and then a 2 cycle. You could have just a 3 cycle. You can have a 2 cycle, and then, oh, sorry, that's a 3 cycle again. I think it's just a product of 2 transpositions, disjoint, and then you can have a transposition, single transposition, and you can just have the identity. Okay, so now let's count how many there are of each type. So there are well, with this in A5, because we're doing A5 specifically, so this is, or sorry, S5. In S5, there's 5 letters, so all 5 letters are going to go in there. You can permute them any which way you want, so that there's, you know, a priori, there's 120 to consider, so it's 5 factorial. But any reordering, like cyclic ordering, is the same one, right? Because a cycle like 1, 2, 3, 4, 5 is the same as 2, 3, 4, 5, 1. So we divide by 5. Each one is represented 5 times, so there's 24 of these. Okay, and why did I write the same thing twice here? That was foolish of me. Okay, so 4 cycles, it's the same thing. So you can first fill it with 5 choose 4 different ways, like just choose the 4 numbers. Then you can permute them any which way you want, but every 4 of them are going to be the same. So we get 5 choose 4 is 5. This is 3 factorial, which is 6. So 5 times 6, which is 30. Okay, now 3 and 2, there's actually, okay, there's the same amount of both of these ones. Okay, there's just 5 choose 3 to fill the first one, and then the other 2 have to just follow. So there's only 5 choose 3 ways. And then for a cycle, like say you have 1, 2, 3, you could also have 1, 3, 2, and that's the only other way you could have it. So you just times 2. So 5 choose 3 times 2 is 20. And it's the same thing here, right? Because the choice of the other 2 were forced. So it's really the same as this. There's a 1-to-1 correspondence. So there's also 5 choose 3 times 2, and that's 20. Then how about just the 2 disjoint transpositions? This one's actually kind of tricky, because if you think of it the first way, like, so you get, there's 5 choose 2 ways to pick the first 2 numbers. Then there's 3 choose 2 ways to pick the second. And so you might think that this is 5 choose 2 times 3 over 2, 3 choose 2. So that's 10 times 3. No, sorry. Yeah, 10 times 3. So that's 30, right? But we have actually counted everything twice, because that counts like 1, 2, 3, 4. But it also counts 3, 4, 2, 1, which is the same thing, because disjoint transpositions commute. So we have to divide by 2. So we divide by 2, and that gets 15. This one's easy. That's just 5 choose 2, which is 10. And the last one, there's only 1 of them. Okay? So as a sanity check, let's add up all these numbers. So 24 plus 30 plus 20 plus 20 plus 15 plus 10 plus 1. Okay? This should add up to 120. So we have what? 54, 74, 94, 100, 94, 109, 119, 120. Okay? Now, what are the even transpositions? The even transpositions are, well, we're kind of getting into it. So AN is a union of some of these conjugacy classes. Now you have to have the identity, right? So let's pick a different color. You have to have the identity, so you must have this conjugacy class. And then, because you're a non-trivial normal subgroup, you have to add up to something that divides 120. Now, all the divisors of 120 are, well, okay, so I'll show you how to get 60. So you get 60 by, these are all the even transpositions. So, I mean, sorry, the even permutations. You can't have a transposition, but you can have the product of 2. And then you can have 3 cycles. And then you can have, so what is that? 1, 15, so that's 16 plus 20, 36. And then that's all. You put the 5 cycles in there, and that's literally the rest. Right? A 3 cycle is even, and then a transposition is not. So this is odd, and then a 4 cycle is also odd. Okay, so these are the even transpositions, and so it's, what is it, 20, 20, or 24, 20, 15, and 1. That adds up to 60. Now, if you try to, if you suppose that there were some other non-trivial subgroup of S5, then there'd be a subgroup of A5, like a non-trivial one, which means you would have something that has cardinality. Let's write all the divisors of 60. So 1, 2, 3, 4, 5, 6. I should do this in pairs. 60, 30, 20, 15, 12, and 10. And I think that's all of them. Now, you have to have 1. So once 1 is in the sum, you can't actually get any of these other numbers, right? For example, you can get 1, that's fine, but you can't get 2, you can't get 3, 4, 5, or 6, because the next one is 10. You can't get 10, because you can only get 11. You can get 11, but you can't get 12. You can't get 15, you can get 16 if you want. 20, yeah, you can't get either, right? It's really easy to start striking all these out, which means this shows that A5 is simple. Okay, so it's like by brute force. Okay, so this takes a while. I don't know if I would like yeah, I guess I would do this on an exam, but what I do know is like each question should take you half an hour, which means I think, you know, I don't know how long this video has been, but this is brute force, but at least you don't have to like remember things so much as like you just remember the idea. And the idea is you enumerate all the cycles, and then you show that if you get a union, you can't make a union of this in a non-trivial way, except for to take the alternating group. Okay, and the last step is kind of nice, actually. I thought it was pretty slick, and I've definitely never seen this last part before. We want to show that an is simple for n greater than 5, and we now know that a5 is simple. Okay, so let n be a normal subgroup of, or sorry, I mean, what did I say? Yeah, okay, an is simple. I guess there's another, okay, whatever. Let n be a normal subgroup of an, okay, that is non-trivial. Non-trivial. Okay, so there's some sigma in n, and sigma is not equal to the identity. Okay, so since sigma is not equal to the identity, if it's a 3-cycle, so if sigma is a 3-cycle, we're done. Right? By lemma 1, or the part 1 here. If you contain 3-cycle, then n is an. Okay. So if sigma is a 3-cycle, we're done. If it's not a 3-cycle, then it has to have at least 2 disjoint transpositions. So, you know, sigma has to have some transposition, some other transposition. And if it is a 3-cycle, we're done. If not, then we can find then I believe that sigma has to move at least 4 things. Okay, so like sigma has to have 1, 2, 3, 4. Okay. Is that correct? I'm actually starting to, you know, have a bit of crisis of faith that this is like, it has to be exactly, has to move. If you only move 3 things, you're 3-cycle. So yeah, okay, sorry. If you only move 3 things, you're 3-cycle. So if you're not a 3-cycle, you have to move at least 4 things. Or you could move 2 things, right? If you can move, but then you wouldn't be an even transposition or an even permutation anymore. Okay, so it moves at least 4 things. So sigma moves at least 1, 2, 3, and 4. Okay. Now what do we do? Okay, so I seem to remember that you need to now take sigma and make a commutator, okay, with a 3-cycle. And I think the 3-cycle is, it moves at least 1, 2, 3, and 4. So, okay, the 3-cycle, I really don't want to go look at the notes. Okay, so let's look at this. So sigma, 4, I think it was 4, 5, 6. Sigma inverse, and then 4, 5, 6 inverse is 4, 6, 5. Okay. Okay, so this should be an element of n, because, okay, first of all, yeah, okay, why is this an element of n? Let's call this tau. Let's call this tau, and we see that, okay, sorry. This part here, okay, is sigma inverse. Sigma inverse is an element of n because it's sigma is an element of the normal subgroup n. And then you conjugated it by something. And so it's still an n, times it by sigma, it's still an n. So tau is an n. Okay, on the other hand, this thing here, okay, is the conjugate of a 3-cycle, which means that it in itself is a 3-cycle. So you have a product of 2 3-cycles. Okay, now the product of 2 3-cycles, we just have to figure out the coefficients here. What am I trying to figure out? So this is 4, 6, 5. If any of the numbers 4, 6, and 5 are in here, then we're in good shape. I just want to reason that one of them has to be in there. So 4, sigma moves 4. Sigma moves. Yeah, the problem is I'm worried what happens if sigma moves 5 and 6 as well. I'm not sure I thought about what happens if this happens. 4, 5, and 6. So sigma fixes. Can we say what sigma fixes? So if sigma's a 3-cycle, we're done. If sigma's not a 3-cycle, then yeah, what if sigma moves everything? Say sigma moves everything. What happens here? So 4, 5. Can we say that at least one of them moves? So sigma moves 4 to something. Let's try and figure this out. So sigma moves 4 to something. Let's say sigma moves 4 to sigma 4. That's literally by definition. Okay, so sigma 4. So 6 goes to 6 goes to, we should put sigma 4 somewhere. Let's put sigma 4. Let's call sigma 4 5. Okay, let's say sigma moves 4 to 5. Oh, can we do that without loss of generality? No, we can't, right? Because 4 could be one of, 5 could equal 1, 2, or 3. That's not allowed. Okay, so there's a little snag here. Sigma 4, 5, 6, sigma inverse. I feel like it should be quite easy. I'm just not seeing how it happens here, that we want the support, like these 3 numbers, one of them to be 4, 5, or 6. If we can have that, then we're done. And why don't I continue the proof? Assuming that. Okay, so we'll just assume that one of these is 4, 5, or 6. Then tau moves fewer, or sorry, 5 or fewer. 5 or fewer symbols. So tau is an element of A5 subgroup of n. So there's a copy, not n, sorry, of Sn. So there's a copy of A5 in Sn, obviously, by taking the symbols that tau moves. And tau is an element of A5 because it's an even permutation, which means tau is in n intersection A5. Now, which is obviously as a subgroup of Sn. But n intersection A5 is a subgroup of A5, a normal subgroup of A5. So since it's a normal subgroup of A5, and we know that A5 is simple, n intersection A5 must equal A5. Okay? And so which means A5 has to be a subgroup of n. You know what I mean? Okay, and if A5 is a subgroup of n, well, you know, in particular, since A5 has a 3 cycle, n has a 3 cycle, and if n has a so n has a 3 cycle, and thus n equals a. Okay, so that would be the end of the proof if we can just show that one of these numbers has to be one of those numbers over there. I'm absolutely sure that we can take this 3 cycle so that yeah, I'm absolutely sure we can. So where does 1 go? So 1 goes to sigma 1. Okay, we just want sigma, this thing, and then sigma inverse to not be the identity on something. So say sigma 1 will bring, okay. Sigma inverse will bring sigma 1 to 1. Then we want to bring 1 to 2, and then 2 brings sigma. Oh, it's not going to bring it to sigma 1. Okay, cool. So we've done it. Let's just say these numbers, let's make these numbers. Okay, let's redefine tau entirely. Okay. So we have, so it should be sigma, let's say sigma 1, sigma 2, sigma 3, I don't know. Okay, and then sigma inverse, then sigma 1, sigma 3, sigma 2. Okay, so let's try and, this is a product of 2 3 cycles. Now the second one is just this, right? So sigma 1, sigma 2, sigma 3, sigma 2, and we just want to show that one of these numbers shows up here. Am I? Okay. Well, let's see if we did it right. So sigma 1, okay, gets brought to 1. Okay, sorry, we also need 1 in here. So let's not do sigma 3. Let's turn that away. Sigma 3 disappears, and we need a 1 somewhere. So sigma 1 gets brought to maybe this is different. Sorry, I'm going to just use lots of, this is trial and error, and this is kind of how you come up with a proof on the spot that you're supposed to already know, but maybe you've forgotten. So I think, so sigma inverse brings sigma 1 to 1. And then we want 1 to go to something that is moved by sigma and not to sigma 1. Okay, so let's go here. So 1, let's put 2 here. Amazing. So I think that's it. So sigma 1 and then 2 1. And now we change this. And if you've seen it faster than me, I'm sorry for what must be a very frustrating experience. If you haven't seen it yet, I'm going to explain right now. So we want to show that this 3 cycle here has something in common with this 3 cycle here. And we're going to show that it has sigma 1, okay? Because sigma 1, once you take sigma inverse of it, you get 1. Then 1 goes to 2 here, and now 2 is moved by sigma. So sigma 1 goes to sigma 2. Okay, and then who knows what sigma 2 is sent to? Okay, we don't actually care because the point is sigma 1's here, sigma 1's here, which means the total number of symbols that this permutation tau moves is 5 or fewer. Okay? And since tau moves 5 or fewer symbols, it's an element of A5 as a subgroup, viewed as a subgroup of Sn. And because A5 is, we know, is simple, n intersection A5 has to be A5, and so n equals an. And so we proved that the alternating group is simple by proving by brute force, making a brute force proof of the A5 case and then extending it to the larger n. Okay, so that's the proof of the simplicity of the alternating group. And there was a little bit of sag in there, but hopefully it shows how you can kind of come up with a proof. It's like I had a playlist called Real Time Mathematics back in the day. I don't know if this counts as real time mathematics, because, well, it is real time, but I did like look up the proof beforehand, so it's not like I'm trying to figure something out I've never seen before. But okay. Anyway, maybe I'll make a new playlist called Study With Me, and I'm gonna spend like a whole year studying for these exams. And it's not my primary goal because these exams are, not honestly. If it was my primary goal, I think it would take like a month of like actual studying to like do their PhD entrance exams. It would probably take like a month of dedicated study to like to tackle these, but I'm gonna do it slowly. I have a whole year, so I'm gonna just do it slowly. And maybe every time I see something interesting like this, I'll try to like regurgitate the proof without looking at my notes. And so that's like practice for the exam, and also hopefully interesting for you guys, because hopefully some of the ideas of how you would reconstruct this, or how you would like, what do you have to remember so that you can recreate this proof? Because you're not obviously going to remember everything, but you obviously can't remember like just nothing, because to come up with something like this by yourself, you have to be, well, this is a proof of Galois, right? So some amount of your prowess must be Galois level if you're going to come up with this completely from scratch. So, okay, I'll leave you there. Have a good night.